Good evening, everyone. Welcome back to the Astro Imaging channel. I hope everyone's having a nice Veterans Day holiday weekend so far. We've got another great show for you tonight. We've got Ron Breacher here, and he's going to talk about long focal length imaging with his 14-inch Celestron Edge HD. But before we get into Ron's presentation, I'll just go over a little bit about the upcoming calendar. Let me pull that up here. Share here. All right, so tonight, as I mentioned, we've got Ron Breacher. Then the next couple of weeks, we'll have some processing demos. I'm going to do a processing demo next week on some LRGB data, and then Molly, the following week, will do a demonstration on some COMET data. So that should be fun. And then as we're getting into this time of year with the holidays, with so many of us traveling and our family in town, out of town, go here, go there, everybody's kind of scattered. So we're going to take some holidays off here. So the December 1st, no show. That's the Thanksgiving weekend. Thanksgiving's pretty late this year. So, and then we've got the next week, Tim Martin will be back, and he'll be talking about image processing. So we kind of got an image processing theme going here for a little while. And then Alistair Simon will be here, and he's got a really neat mosaic, this giant mosaic that he's recently completed. So he's going to come and tell us all about that. Then the last 2 weeks of the year, no show. We got Christmas weekend and New Year's weekend. And so then we'll be back on January 5th. We don't have a guest lined up yet, but I'm sure we will get one between now and then. And then Cheryl Wilcox and Alan Friedman will be with us to talk about solar imaging, which we're all excited to see. And then Dustin Brimbury will be with us more about NINA. So that's what we got coming up. And as always, anybody out there, if you've been thinking about a presentation, something you'd like to share on the program, just drop us a line on the website. We'll get in touch and get you on. So let me stop sharing the calendar here. Right, so that then brings us to tonight's presentation by Ron Breacher. And Ron is one of our favorite guests here on the Astro Imaging channel. He's been on a number of times, always a good time. We always learn a lot. Tonight, he's got something a little different for us, whereas Ron frequently talks about image processing. Tonight, he's going to talk about data acquisition, and particularly some of the challenges that he's faced working with the 14-inch Edge HD. So, Ron, if you're ready, I will get out of your way and hand it over to you.
I'm all set. Thank you. I just want to say before I start the presentation, just to everybody on the screen here, thanks for having me. This is one of my favorite places to talk. So I will share my screen. And you should see my slides. Can somebody just confirm that for me?
Yep, we got it.
Okay, great. So 4 meters and counting is the name of my talk, and that refers to the focal length of this telescope that you see on the right-hand side of this slide, 3,912 millimeters, so just about 4 meters. And I say and counting because who knows what's next, right? So this is just an overview of the talk. It is November 10th, it's Veterans Day weekend, and so I just want to acknowledge that. Talk about my equipment for a moment, and then my strategy, the way that I approach deep sky imaging sort of in the long term. Then we'll look at the impact of focal length and talk a little bit about sampling, oversampling, undersampling, whether any of it matters. And then I want to talk about some specific challenges that I had at 4 meters focal length that were tougher than at any other focal length that I've imaged at. And then, if you'll indulge me, I'm going to share with you most of the images that I've shot in the last 15 months or so. And I won't dwell on most of those images, but I do have a few that I want to talk about a little bit more. So I just wanted to acknowledge Veterans Day. We call it Remembrance Day here in Canada. And a lot of the people in this hobby are my age, give or take 10 or 20 years. And there's nobody our age that doesn't have a personal memory of somebody that helped make the world the way it is for us today. And so I just wanted to acknowledge that. So here's the equipment that we're talking about. I'm in the photo for scale. Uh, this is a 14-inch Celestron Edge HD, and it's got the aluminum dew shield on it. And although you can't see it right against the corrector plate, in fact, replacing the original ring that holds the corrector plate, there's a dew heater ring. Prima Luce gave me a bunch of stuff to use with this telescope. So I have the low profile Astro focuser and rotator, the Arco rotator, a flat panel, which was the only way I could successfully acquire flats with this telescope. Sky flats didn't work well. T-shirt flats didn't work well. Not sure what it was, but the flat panel approach did work very well. I'm using an Eagle 4 Pro computer. It's mounted on the top of the tube over here to control everything. I have a QHY 600 mono camera with a filter wheel. I've got Octolong filters, LRGB, and 3 nanometer SHO. Also a QHY guide camera and an off-axis guider. And turns out we're going to talk about them. That becomes important. And it's all riding on a Paramount MX that I've had since, I want to say 2011. And it is a very reliable, excellent mount. So here's my long-term strategy for deep sky imaging. And obviously, the very, very beginning of my journey, I didn't have any equipment that I could sell. But ever since I've started, I'd get to the end of a cycle like this and I'll sell any unused equipment, buy a new scope or camera, whatever I might need, image objects that will fit in the frame for a few years. And I'm aiming for something that's, half to 2/3 the size of the frame. So I don't have to worry too much about corner artifacts or perfect replication of position from night to night. And then I'll just shoot objects of that size for a few years from my observatory. And so I have a pretty good view from the north to about declination minus 15 in the south. And so after 3-4 years from my house, I run out of stuff to shoot for that equipment. So I repeat, I basically sell any unused equipment and start over. Now I've got, under repeat, I've got beware of the law of unforeseen consequences. So sometimes you go for an equipment change and it turns out that if you change one thing, you have to change another. So if you decide to go, if you're running on a relatively small setup and you decide to get a big refractor, the law of unforeseen consequences might mean you need a new mount. So things can very quickly get out of hand. So plan your whole system together. And I guess if you're just starting out, this is just another great argument for putting the mount first. Put most of your money into the mount because it could last you a long time through some of these equipment changes. So my telescope apertures and focal lengths in millimeters have been 60 millimeters. In parentheses, I have the focal length. Some of them are dual because they're with or without a corrector. So 60 millimeter, my FSQ 106. I have a Esprit 150, a 6-inch refractor. I had a 10-inch ASA that operated at 900 and 1700 millimeters. And now, kind of off the chart, 350 millimeter, it should be 305 millimeter, 14-inch telescope. And
Ron,
yeah,
when you say unused, you don't mean equipment you never got around to using. You mean stuff that you've decided, now that I'm going to the bigger
Yeah,
focal length,
stuff that's sitting in a box.
or stuff that will be sitting in a box because you bought the new telescope?
That's what I mean, yes.
Yeah, okay.
Yeah.
So you only have the 4,000 millimeter scope now.
Okay, now you're embarrassing me, Alex. That's not true.
How many of these do you actually still own? Come on, Ron, we expect truth.
Okay, so first of all, I have two that are actively in use right now, because riding on top of the 14-inch, I have a 60 millimeter Takahashi refractor with a one-shot color camera. So when the seeing is bad, I use that telescope. When the seeing is good, I use the 14-inch. Beyond that, I have an FSQ 106, which is in a box. I'm not selling it because I'm putting together a portable rig, and it's going to be at the heart of the portable rig. And I have a 150 refractor, which is probably also going to be part of that portable rig. I want to go back to that two-scope system. So that's all the imaging scopes I have. Then I have a homemade 10-inch reflector for visual, and I have a 20-inch obsession for visual. And my wife has a Questar. Okay, I feel like I confessed.
To tell the truth is fun, isn't it, Ron?
It's really liberating, Alex. I feel so good. Thank you. All right, let's talk about the impact of that crazy focal length. So focal length really affects two main characteristics of an image. One is the field of view, which when you think about field of view, think about how much sky fits in the image. It's also affected by how big the sensor is. But the concept is how much sky fits in the image. The second thing that's impacted by focal length is how much sky fits on one pixel. And that's what we refer to as image scale or pixel scale. And that's also affected by the size of every pixel. So let's just look at that a little bit more closely. So this is the impact on field of view of focal length. And this is just a range of focal lengths that you might find on a DSLR, from very wide field at 18 millimeters, increasing up to 300 millimeters. And you can see that as you increase that focal length, the field of view becomes smaller. You seem to be getting closer to the object. And that's exactly what happens with my big telescope. So if you imagine now 3,900 millimeters, 13 times more magnification than you see in this image on the lower right. Now we're just going to get a much smaller amount of this picture into the field. So that's how field of view, how focal length impacts field of view. The other impact of focal length is on image scale. So imagine a small telescope on the left and a big, long focal length telescope on the right. Sorry, I've got that. Have I got that the other way around? No, that's correct. Basically, the focal length means you're going to have way less sky. Wait, I'm getting kind of muddled here. I want to just think this through. The impact on image scale. So the longer focal length has a much finer image scale. There's more pixels that capture the same size of field of view. So on the right is the long image scale. On the left is the short focal length. And this is probably best illustrated by just showing you a few different images shot of the same object, but at different image scales. So this was shot with, I think it was an 85 millimeter lens on a DSLR, and the image scale is about 10 arc seconds per pixel. If you increase the focal length, so so that you just capture this. This was captured with an FSQ 106. And so now we're at 3.2 arc seconds per pixel, roughly three times the focal length, roughly three times the focal length. And you've got basically less sky in the image and more detail visible.
I'm the guy running it right
and
now.
if we now go up to
Can I call you when I finish?
10-inch ASA that I told you about. So if we go up now to 1700 millimeters,
oh, will do. Okay,
we're
okay.
at 1.1 arc seconds per pixel. Less sky still and much more detail visible, because the same number of pixels are being devoted to less sky. That's why you reveal more resolution. And we can go even closer. So my wife actually pointed out this little structure here. I didn't find a catalog number for it, but she said it looks like the head of a lizard poking out of a cave. And so I call it the Lizard Head Nebula. And this is at 0.4 arc seconds per pixel. That's the resolution of the 14. This was taken with the 14-inch telescope. So you get the idea of how focal length is affecting the not just what you get in the frame, but the quality of the amount of resolution that's revealed, the amount of detail that can be revealed. So here's the problem that you have to solve when you're trying to get the most out of the sky. The question really is, how many square pixels does it make to make a round star look round? Let's ignore the first row in this diagram for a moment and look at the second row. This is a scale of, this is a situation where a star is falling on 1 pixel. And it's centered in the first case on the left. On the right-hand side, it's on the vertex. And you can see that that's not enough pixels to make the star look round in an image. Obviously, 1 million pixels is too many. So the question is, how many do you need? When you go to a third, basically what this is a third of the seeing. So you're allowing the star to spread over 3 pixels. Whether the star falls in the center of a pixel or at the vertex or the intersection between 4 pixels, it's going to look pretty round. And that's essentially what the Nyquist theorem says. It says that you need an image scale of a third of the seeing to capture all the detail. Now, some sources would say that for DSOs, particularly with CMOS cameras, you really need more to capture all the detail. And I'm just going to go on record saying that based on my own experience, I am one of those sources. I can get better results with an image scale that's less than a third of my seeing. And I'm going to show you some examples in a moment, and we'll talk about that. So I just wanted to, I use full width half maximum as a proxy measurement for seeing. And in Guelph, where I live, Guelph, Ontario, my average seeing is around 2.5 arc seconds. On the best night I've ever had, it was around 1.6, and it's never much worse than 3.2, 3.5 maybe. So my optimum image scale, if I go to a quarter of the seeing, is at 0.4 to 1.2. And here's some image scale examples with my own equipment. And I was at, for a while, I was using a 6-inch Skywatcher, and I was at 0.72 arc seconds per pixel. Fantastic telescope, gave great results. And this is less than a third of my average seeing, 0.72 arc seconds per pixel. And yet I get better results with the top example, even when I bin the pixels, so instead of 0.2, I run at 0.4 and I get better results. So I know that I need better than a third of the seeing to get the best that the sky will give me. So the question is, why don't I run at 0.2 arc seconds per pixel? Well, the answer has two parts. The first part is I've done the experiment and I don't get better results. The second part is that binning the pixels makes the scope seem to be faster than it is. I can't really quantify that, but instead of F11, it's running faster, maybe more like F5, F6 to 7 in that range. It just feels way faster than F11 and at no loss in resolution that I can detect no matter what I do. You can see some other really popular combinations. So I had a 4-inch tack with a QHY 367C Pro. These are 4.88 micron pixels, so intermediate in size. This gives me right around 2 arc seconds per pixel and a big wide field. This is big enough to frame the Veil Nebula. 1.9 arc seconds per pixel is clearly undersampled based on the calculations that I showed you. But who cares? Images with this setup look fantastic. And the first picture I showed you of the North America Nebula, that was 11.7 arc seconds per pixel, more than 24 degrees available in that pixel across, and still does a great job. So let's talk about optimum and undersampling and oversampling. So image scales anywhere from about 0.5 arc second to 5 arc seconds per pixel are fine for deep sky objects, but you might see that the stars are kind of blocky. The smallest stars, if you zoom way in on them, they might start to look a little bit blocky above 2 arc seconds per pixel. That doesn't matter for some kinds of shots. So if you're shooting a skyscape, I don't know if you've ever seen Carrie Ann Leckie Hepburn's skyscapes at Easter Island or the Milky Way shots that she does. They can be 30 arc seconds per pixel or even higher, and it doesn't matter because of the nature of the subject. So it's more important that the object that you're interested fit on the sensor than it is that you try to optimize image scale. Now, on the other hand, if you're like me, you've got one telescope. I can't change my lens easily. I've got one telescope that I'm going to use for a few years. I have to pick objects that fit on my sensor. Okay, let's talk about undersampling and oversampling. So if you're undersampled, what that really means is that you haven't got enough pixels to capture all that the sky will give you. And that means the tiniest stars are likely to be square upon close inspection. Let's remember that most people look at most of our images on their phone. So I'm not too worried about undersampling, particularly when you're shooting really big objects. But there will be limited detail that's visible in those deep sky objects. One solution is to upsample and recover resolution using drizzle processing, which will help round out stars and restore some of the detail. And by the way, everybody should be using drizzle processing all the time. You should just not always upsample with drizzle. The bottom line is, don't worry too much about undersampling if your intention is to shoot big, wide shots. Big things like the Andromeda Galaxy require a wide field. And if you're not going to get it with a small telescope, you're going to have to do a mosaic, which may be harder. Field of view is more important than image scale a lot of the time. So always put that first. This image is undersampled at 1.9 arc seconds per pixel. And I don't think I don't think it looks undersampled. I don't think you can see that the stars are blocky. But if I were to zoom way in, if I wanted to pixel peep, you might see some stars that didn't look perfectly round. So,
Ron,
yes.
if we want to find out if something is oversampled, we zoom in and we
and
look
see
for
if
the
there's-
blockiness you had in your chart with
Yeah,
okay.
yeah. Look for blocky stars, and
That's
maybe when I get through the talk, if there's time, I could show you an example of that.
That's
'Cause I have-
undersampled. Right.
That's correct.
Right. Okay.
Yeah. Okay, so oversampling is a whole different problem. So first of all, remember I talked about the law of unintended consequences. You want to get that big scope. If you're oversampled, you probably have more telescope than you need, and that means you probably paid more than you needed to for your mount. Or you might need to go and get a mount if you don't have one big enough already. The other cause of oversampling can be buying a camera with pixels that are just too small. Small pixels are less sensitive. This is much more of a factor for CCD. There's a lot more benefit to binning your pixels for CCD, but there's still benefits, or I'm seeing benefits, at least on my system, even for CMOS. If you're oversampled, your tracking errors, if you have any tracking errors, if there's any polar misalignment in your system, it's going to be more obvious in terms of oblong stars and jittery guiding and all that stuff. And effectively, if you're oversampled, you have empty magnification. It's like pixelation. It's like if you take a JPEG and you blow it up too much, eventually you'll just see the pixels. That's empty magnification. And the same thing can happen at acquisition. So really what we're trying to optimize is having the right number of pixels to capture a round star on square pixels, and maybe a little more than you need, but not too much more than you need. One solution, if you find yourself oversampled, as I did, is to bin your camera. That will help you optimize resolution, and it will increase sensitivity somewhat. Bottom line, though, is oversampling doesn't provide resolution beyond what the sky will give you. The goal in astronomy is to control the things you can, reduce the influence of the things that you can control. You can't control your seeing, although maybe these days you could set your telescope at a remote observatory. But if you're observing like I am from my home location, I can't control my seeing, my weather. What I can do is control my acquisition, how I set my camera, and so on. So I've chosen to bin, and I'm at 0.4 arc seconds per pixel, which is at least 5 times my average and 4 times my best night ever. So I'm in pretty good shape. Some of the particular challenges that I've had with this long focal length setup are collimation, guiding, and dealing with seeing. So let's talk about collimation first. So initially, I had a really hard time collimating this setup. And part of the problem was just the bulk of the thing. So it weighs a lot, and it's a big tube, and my pier is 4 feet off the ground. So the top of the tube with the dew shield on it, it was very difficult for me to get my arm down into the tube with a screwdriver in the dark and turn those black Phillips screws. Really, really difficult. Guiding was also problematic. Seeing, the results obviously depend on good seeing. So let me show you how I dealt with all of these problems. So this is what we went from, this is what we went to. Collimation. I tried several different hardware and software tools. So I used the Hotech collimator. The left side graphic here shows the OCal. I don't know what that stands for. OCal 3 Max collimator that I got from Astro World Telescopes, Dan Higgins in New York. And you basically attach this to the back of the Schmidt Cassegrain. It's got a little sensor in it, and it helps you collimate electronically, and you can do it during the day. I did get close with this, but it wasn't perfect. I had to finish using the stars. Oh, by the way, you might be thinking, why didn't I just take the dew shield off so that it was easier to get at those screws? Well, this is a very heavy telescope, and it's got to be very precisely balanced. That's an aluminum dew shield. It's not just foam rubber or something. It's hefty. And if I take it off, I would strip all the gears on my mount. So to track the stars, I have to have it balanced, and I had to have that dew shield on. It was very difficult, as I said, to get my arm in there. So what I did is I swapped out the screws, the Phillips head screws, for Bob's knobs. Maybe a lot of you have heard of them, but I hadn't. And they are fantastic. So I didn't need to use a screwdriver anymore. Once I figured out which screws to turn, I was able to just turn them with my fingers, and it made finishing collimation really, really easy. Guiding was problematic. So at first I tried using a regular OAG. You look at the second bullet, I could sometimes never get a star. I could rotate a little bit, but then I'd have to shoot new flats every time I imaged. And, you know, my goal is, I think I already told you, flats were problematic for a while as well, until I got that Prima Luce Giotto. So I tried an external guide scope, and that proved to be completely ineffective because I guess because of differential movement of the optics. So you have to stay with an off-axis guider with a Schmidt Cassegrain telescope. So what I did is I got a QHY 585 sensor, which is this guide camera up here, and I got their large prism off-axis guider. It's called the OAG M Pro. And now I never have any trouble finding a guide star. There's also a much bigger hole going from the light path off the prism to the sensor. The hole is a lot bigger. So initially I just replaced the sensor, and guess what? I just had a round, small illuminated area with no stars in it. Anyway, this new setup works great. Let me show you. Oh, I wanted to just say about seeing. My solution for seeing, I put a little telescope on top, and when the seeing is bad, I don't use the big telescope. I use the little telescope. So this is just going to be a walk through some of the images I took with this setup over the years, some of the things that I learned as I went along. This is the very first thing I shot with this telescope. Obviously, it's the Crescent Nebula. I just wanted to direct your attention to the bottom right below the label NGC 6888. Do you see the little spikes coming out of the bright blue star around 2 o'clock especially? It took me about a month to diagnose that. It turned out that that was coming from the dew heater ring being too hot and causing a distortion in the corrector plate. One of the things this telescope does really well is little things, and it opens up basically a whole catalog of small objects you can shoot, and I'm just going to highlight a few of them here. Able 84 planetary nebula, just 2.9 arc minutes on the long extension. This is just 1.4 arc minutes in the long dimension, NGC 7008. And even smaller, this might be the smallest thing I've shot, I think. Just 38 by 35 arc seconds, NGC 40.
Ron, are these being cropped?
They're cropped a little bit, but not much.
Okay, how big is your sensor, generally speaking? Full frame?
It's not big enough to get a half moon. Yeah, the sensor is full frame. And it would maybe barely get, it's probably, maybe 30 by 20 arc minutes.
Okay.
Would be-
We do have a question. Are you
Yeah.
familiar enough with planetary cameras to tell Tarek? He wants to know, why don't you use planetary cameras? They seem to have larger sensors, he's explaining.
No, not larger. I think there's one planetary camera in particular that has larger pixels. I'm trying to remember what size those pixels are. It's the IMX 432. But yeah, he's asking about some planetary cameras have larger pixels.
Do you have any thoughts on that, Ron?
I don't know of any planetary camera, or maybe he's talking about the guide camera.
Don't know. I don't know that planetary cameras have
there's
large sensors.
There's no planetary camera that I'm aware of that has a full frame sensor.
No, yeah, they don't do that.
They don't do that. They're all small.
Right. He's talking about the pixel size, not the sensor size.
Yeah, he's talking about pixel size.
Yeah, like the 432, it has 9 micron
Okay,
pixels.
I understand, because I didn't buy a camera when I bought a scope. I made do with what I had, which is what most of us really have to do, right? I already had a camera that worked very well. It's just a little bit oversampled for this scope. Bin it. You don't have to go out and buy a new camera. And you know, I always tell people the best equipment is the equipment that you have, right? If you're going to use what you have, that's fine. And there's a lot you can do to make your camera more usable, especially if you're oversampled just by binning.
A couple others, I think, maybe while we're here. Just to confirm, Hamza wants to know if you're using the QHY 600 and is it binned at 2.2 with this telescope?
It's been 2x2 with this telescope, yeah.
And it's the 600. Okay.
Correct. So my image scale works out to 0.4 arc seconds per pixel.
And I think that's the question.
Okay,
That's the questions, Ron.
Ron,
Yes.
you said that it appears to improve the speed of your telescope when you bin 2, but you're just averaging those 4 pixels. So should that be?
That's kind of how it works with CCD. I don't think I don't really understand the math. I'm telling you empirically, it's faster. Like the signal to noise ratio is better. I can't really I think I said it before. I can't really quantify it, and I don't understand the math well enough to answer the question credibly.
Yeah, as we discussed earlier, this bin 1, bin 2 is a good subject for another talk.
Well, no, but Eric, I can tell you there's definitely in my case, there is an advantage in apparent speed from
That's really
bin 2
weird.
with no loss in resolution.
I could see an SNR argument potentially, but you're not summing pixels the way that you do on a CCD.
Agreed.
Right. You're averaging pixels.
Yeah.
Subject for another talk.
Yeah.
I
Yeah.
got a few questions coming in. What mode and gain do you use on your camera?
I use double correlated sampling, high gain mode.
Okay.
I think CMS one is what it's.
And we're talking, Tarek wants to know if we're talking just pretty much DSO in your presentation.
All DSO.
Yeah, because if we were taking planets, 4,000 millimeters would be pretty cool. You just have to be able to have a good aim on that sucker.
Yeah, well, Chris Go, Sean Walker, a bunch of my friends that do really good planetary work, they use C14s.
You know, that brings up another question. So you use the same gain for narrowband as you do for LRGB?
I do. I don't shoot luminance though. Rarely.
For RGB.
Yeah.
So there's a noise component. Do you shoot them at the same exposure, same time?
Yep. 5 minutes all the time. 5 minutes, 5 minutes, 5 minutes. If I'm shooting narrowband and I'm shooting a faint object and I need more time, I get more time. Stefan's quintet.
Yeah, I think we're finished with the questions from the.
Yeah,
from the-
interrupt me anytime, no problem.
Yep.
So, so to your question, Eric, this is, I shot SHO RGB in 5-minute exposures and made 3 different images. The stars are the same in all of them. The one on the right is RGB enhanced with H alpha. The center image is the Hubble palette with RGB stars. And the image on the left is the 4-ax palette. So also sulfur, hydrogen, oxygen, and RGB stars. And this is IC417. This is in Auriga. This is well placed for imaging, coming up late in the evening, right now in the Northern Hemisphere. Go get it. It's a beautiful part of the sky. And one of the things I love about this telescope is the amount of detail you can reveal in galaxy. Like I've shot this galaxy many times before, but I never got detail like this. It's crazy. This is also, so not particularly small, 2.5 arc minutes across, but I just never saw it before. And I came across it in a catalog, thought, well, why not shoot it? All the pictures, when I went online, all the pictures showed the ring, but they didn't show the stuff around the ring. So very cool to go long on these objects. This is Messier 82. Like I never saw it before anyway. And M97, another example of an object I've shot several times, but able to get more detail. This faint oxygen shell, I never captured it before, and a little galaxy over here. Messier 108. Again, I've seen all these. I've shot a lot of these before. They just come out so much, showing so much more. This is an example of one that I could never have shot with any other piece of equipment that I've used, or not gotten a result like this. So this is the Cat's Eye Nebula. And this just shows so much detail, even right down to the core, and it shows all the concentric rings around that core. And the Ring Nebula, one of my favorite visual objects. I've seen the central star once, that I'm convinced where I'm convinced I saw it. But it's really nice to be able to pull out this shell around it and get so much detail in this little 15th magnitude galaxy. And if this is 15th magnitude, what's this little guy over here? And whatever its magnitude is, what's the magnitude of this little thing here? There's so many of these little galaxies. They're everywhere. There's one up here. There's one over here. And yeah, you can do globular clusters too. This is pretty much uncropped. So it's spilling out of the, practically spilling out of the field and showing really fine resolution. Messier 27. Again, I've shot it a lot of times, but not looking like this. This is also the 4-ax palette. So this is sulfur, hydrogen, and oxygen, and RGB for the stars. This is NGC 6914 in Cygnus, and I call it Eyes in the Dark. I think you can probably see why. Again, I've seen this in a wide field before, but it's just got a lot of beauty in its own right. Really interesting how in the right-hand eye over here, how this bridge of red hydrogen seems to cross the blue reflection nebula. I think that's really cool. This is the elephant trunk in 3 palettes. So this is something I've been taking to doing whenever I'm shooting narrowband. I acquire some RGB stars, and if it's a nice natural color object like the elephant's trunk, I get lots of RGB data, and then I make multiple versions of it. So this is obviously the elephant's trunk nebula in IC 1396. And again, 2 narrowband palettes, one on the left, one on the right, and a natural color palette with H alpha in the center. I'm a big fan of open clusters, and I often shoot them during time while I'm either waiting for my main target to rise high enough, or my main target has set and I have an hour or two before dawn. And this triangular cluster is called NGC 2266. That's what I thought I was getting. But as you can see, I got some really nice little galaxies over here and another one up here. And there's a few others around the field. And I haven't tried yet to identify those galaxies. Excuse me, but it'll be interesting to learn about them. This is the Cocoon Nebula. So we're getting close to now. I think I just shot this in September. So the Cocoon Nebula and a beautiful reflection nebula to the upper left, and lots of dust all around. And similarly, the Iris Nebula, and some really nice H alpha stuff that I didn't see in any of my other images of this object. I've seen something like this in some other people's images, but I never caught it myself. So that's always fun. And here's a cool one, just from October. This is the Crystal Ball Nebula. Very tiny little thing. So this image is cropped quite a bit, but again, lots of detail visible here. And this is the iconic Bubble Nebula, natural color RGB, no H alpha added in the image in the center. And then on the left is Hubble palette, and on the right is Thorax again. And this is, so one of the things that I do is with Warren Keller and Pete Prue, we have this website where we teach, it's called Masters of PixInsight. And on November 19th, there's going to be a Photons to Photos workshop where I'm going to be actually processing this data live, starting with masters and making these 3 images or something similar to them. I asked Pete to set up a coupon for us. So if you want to register, go to mastersofpixinsight.com, register within the next 24 hours and use the code Astro, and you'll get $5 off the registration. Okay, I'm getting close to the end, but I want to show you what was maybe the coolest thing that I've done with this scope. This is Able 779. It's a galaxy cluster 300 million light years away. And that's cool, all right. But I use annotation programs to identify these galaxies. And on this particular occasion, I added a catalog I don't usually use. So all of the galaxies that are highlighted in yellow are either in the NGC, the New General Catalog, or they're in the PGC. But the items that are annotated in white are from the Milliquaz catalog, and they're quasars. And quasars are extremely distant. Now, I didn't investigate all of them, but I investigated some of them. And you'll see a couple of circles around these markers down here on the lower right. Let's zoom in on those. So this first one, the top one, you can probably see in the crosshairs, there's that little dot there. That little dot is a galaxy 9.3 billion light years away. And I thought that was probably the furthest thing I had ever imaged until I looked this one up. And when I looked up its redshift and did the calculations, its light travel time was 12.8 billion light years. So just less than a billion years after the Big Bang. So just amazing what this this telescope can pull in. Couple that I have in progress that I'm showing here for the first time. They're not on my website or anything yet. This is the Heart of the Heart Nebula in narrowband. This is just about 2 hours of data. I now have, I think, 30 hours of data, so I'm looking forward to processing it properly. And this is still being acquired. So this shows about 25 hours on, 17 hours on Sharpless 2200. It's also known as the Bear Claw Nebula. I'm now up to 36 hours and 36 and a half hours. And I have a clear night coming on Tuesday and maybe on Wednesday. So hopefully I'll get to finish it then. So if you want to find me, you can find me at astrodoc.ca. If you want to write to me, you can reach me at rbreacher@rogers.com. I love to teach. I teach privately and also the workshops at masters@pixinsight.com. You can look for my writing in Sky and Telescope. And just thanks for having me here on the Astro Imaging channel. I love doing this. Thank you.
Well, thank you, Ron, for being here, and that was really fascinating. So the amount of detail that you pull out of some of those smaller objects with that system, it's
let
blowing.
I know, it's crazy.
We let some questions pile up during the show, during the showing all those beautiful images. So maybe we need to get to them. John at Astro wants to know, how do you measure your seeing so you know which scope is probably going to be best for you that particular night?
I look up I have a couple of websites that I use. One is the Clear Sky Chart, and the other one is Astrospheric. And if the seeing is going to be average or better, then I would use the big scope. If the seeing is below average or poor, then I'll use the little scope.
Okay. Is there such a thing as the Brecher deep field?
No.
Not yet?
It's a rumor.
How long is your longest exposure on a given point?
My longest exposure is 104 hours.
On the same point in space.
On the same object, and that was on the flying bat and the squid.
Damn.
129 and OU4.
Boy, that is a tough target.
That target needs it.
I was lucky. I've seen a lot of people get great results with much shorter exposures now. And I think, again, that's a testament to the new technology. I shot it with a CCD camera, front illuminated CCD camera, right? Now we're using back illuminated CMOS with these crazy quantum efficiencies and practically no very, very low read noise.
It's a tough target when you have a long focal length and you're spreading out that limited light over a lot of different pixels.
Yeah.
It's tough.
One of my buddies, Kenward here, asks, what's the total time imaging for the ring, the picture of the ring you showed us?
I can get that information pretty quick, but I have to look it up.
Okay.
But Just talk among yourselves. Bring on the next question while I.
Da-di-da-di-da. Do you ever play the mandolin or the guitar?
Oh yeah, I do. I do. I play the guitar. I don't play the mandolin, but I have a guitar that sounds like a mandolin. So this is the Ring Nebula Astro Pix.
Do you have a banjo?
I do.
Oh,
I'm sorry, I do.
I kinda
29
want-
hours and 5 minutes on the Ring.
On the Ring. Okay, Kenward, there's your answer. What'd you do about Isaac wants to know how you fix the star spikes from your do ring.
I turned the power down.
That was
I
how
had-
does power make spikes?
I had the same issue. It has to do with warping the corrector plate when it's too hot, except mine persisted when I turned off the dew heater. So I'd never figured that one out. So I just took it off and put a new one on. I put the regular one back on. I gave up.
Okay. Weird.
There's a lot of good talk about this Ron Brecher guy. So did you have the bat lined up where you could show us the bat, or is it ready to go yet?
Yeah, the bat, I did that years ago. Yeah, I can show. Sure. Hang on. I've actually got it.
Dean wants to know, he wants to see the bat.
I'm getting it.
Show us the bat. Ah, perfect.
It's on the cover of the Observer's Handbook.
Uh-huh. And you print all of your really good ones on the front of your books.
Yeah, oh yeah.
That's
Definitely.
great. Yeah, any special processing considerations with high res data?
It's high resolution is a lot less forgiving. There can be more things. There's more things to go wrong. And you can see defects in stars that would just not be visible at lower resolution sometimes. Right? So if you're at lower resolution, say you're at 2 or 3 arc seconds per pixel, like you're using a really nice 100mm refractor, okay, or 80mm refractor, you're at a couple of arc seconds per pixel. If you go a little bit out of focus, I'm talking a little bit out of focus, you're not going to see it. If I go a little bit out of focus, it can make my stars blow tremendously. And that you would think that at f11, the critical focus zone should be really big. You should be able to drive a truck through it, right? Because you're at high focal ratio at f11. Critical focus zone ought to be wide, but it isn't, because the small pixels just the image scale, the 0.4 arc seconds, just reveals that tiny little bit of expansion of the stars that you might not see at lower resolution.
Yeah, the same thing applies to the seeing. A little change in seeing has a dramatic effect, especially on the stars. Not so much on the nebula, but really on the stars.
And that's why I go to the smaller telescope, because it's just not affected by that.
So Ron, your reference to the focus issue kind of dovetails with last week we had George Helios on about hocus focus, and I know you use Nina. Were you able to use the default settings, or did you have to fine tune some of those? What were the things that you found were the tweaks you had to make in that hocus
Well,
focus?
the main tweak I had to make is knowing that I didn't know everything about it, and I had to go online and find a video to tell me what to do.
Even you?
But yeah, even me. But here's the nugget that I found. Focus your telescope. First of all, Nina can only do what you can do manually, right? So first of all, get an image loop going on a star and get it focused as well as you can, watching the number, get the full width half maximum as low as you can. Then figure out the number of steps that you have to go to make it appear a little less focused. That's your step size. And then you need, when you do your, when you set up hocus focus, you want to have usually 4 times that step size as your initial movement away from focus. So start out focused, find out how much you need to move it to make it look a little out of focus. That should be your first estimate for step size.
And you feel like you got it dialed in pretty well at this point? You obviously, the results speak for themselves, I guess.
Yeah.
But it's tough, you know, because with that really long focal length, you've got that narrow field of view, and sometimes you just don't have that many stars maybe in the image, right? So
There's enough. There's always enough. There's always enough. Yeah, you can tell when I'm talking about dialing it in manually, if you have 1 star that you can see, you can get it close to perfect. And then just write down whatever the focuser position is. And then move it a little bit, move it 50 steps at a time till it starts to look a little worse. However many, whatever the difference is, that number of steps, that should be your starting point for step size. And then you can go up or down from there.
Ron, when you're talking about the challenges, I know my eyes are such and my brain is such that I really can't see some of the things that other people say. See that there? See what the problem is? And I go, no, I can't see that. How much zoomed in do you have to be before these things show? I imagine to you, not as much as to me. I mean, you'd have to zoom in pretty far before I could see it. But how about?
I mean, it depends on the nature of the defect, right? So some of them are very large scale problems and some of them are small scale. So the very large scale problems are things like I told you, I tried multiple different ways to acquire flats. And I would always end up with a darker donut in the center of my image, particularly in the green channel. And so that's a very large scale defect. You don't need to zoom in at all to see it. And I found ways to correct it while I was figuring out how to prevent it.
Well, yeah. You spoke earlier of star shapes and focus and things like that.
So Alex, I have a test I call the good from far and far from good test. Right? So here's what I do. I start out by looking at the whole picture. So I'm far away and I see if it looks good from far. And then I zoom in and I look at the individual stars. And that's when sometimes it looks far from good. And I have to start eliminating frames.
Okay. Guys, I think we've got all the questions, right? Anybody else watching the question stream? We got Hamza wants to know if anybody's got a report on the ASA 10 Newtonian, but
I had an ASA 10.
Have you ever had one of those?
Yes.
Oh.
I had a 10-inch ASA 10 and it was a fantastic scope. I think it's down at Chili Scope now. But the cool thing about that scope, it's native f3.8, but it comes with up to 3 different lenses. 2 are correctors, 1's a Barlow. So it can operate at f2.8, f3.6, and f6.8. It's a really versatile scope. Plus, it's carbon fiber. And so it's solid. You don't need to focus it all night. The mirror on that thing was zero dur, which is like a almost 0 coefficient of expansion. So same thing, really, really stable. And the vanes that hold the vanes that hold the secondary, they're paired blades. And they give the most beautiful diffraction spikes you ever saw. They really do. Yeah.
Okay.
But I sold it.
Uh-huh.
Because of what I told you. I shot the Jesus out of the sky with that scope at both. I didn't use f2.8, but I shot at f3.6 and at f6.8, and then I was out of stuff and I sold it.
out of stuff.
I mean, I ran out of targets that were easily accessible.
Run out of targets.
But I sold it. I got good money for it, and I used it to buy a TAC FSQ 106.
There you go.
So,
Yeah, that's a wise approach. So some of us seem to be more into stocking our museums, our equipment museums, and hanging on to things. So, but
yeah.
Yes, I regret selling a couple of my scopes because they're such works of art. I sold my 106 and I wish I'd just kept it.
But if if a telescope is a work of art, then it should be in your living room, not in a box. So that was my criterion, right? If it's in my living room, then it's not just a telescope, it's something. So my wife's Questar is a 50th anniversary Questar. That's never going to get sold, even though it only gets used maybe once a year, right? It'll never get sold because it's beautiful. But the other stuff, the imaging scopes I have, they're all replaceable. You could sell your FSQ 106 and buy another one if you changed your mind.
I did sell it and I didn't, but I got a baby Q instead.
There you go.
By the way, before we forget, when the program is over, you're welcome to stay and chat.
I have other commitments tonight.
all right, well, I think we've. What's that?
No, go ahead.
Oh, I was just going to say, I think we've got all the questions, so we can wrap this up and let you get on to the rest of your night then.
Thank you. I love coming here. Thank you. Good to see you, Alex. Good to see all of you.
Thanks for coming back.
Yeah, absolutely.
We
You
really
too.
appreciate it.
Ron.
Bye.
Are we
Great, thank
wrapping
you.
up? So
I think we are.
time
All
to
right,
say
buddy.
goodnight. Oh, he left right away.
Oh, all right, he's out of
He
here.
was